All right, let's talk about logistic growth. So, unlike basic exponential growth, where the rate of change of a population is directly proportional to a current amount and a population can grow without bound, logistic growth is a little bit different. It's capped by what's called a carrying capacity. So, with exponential growth, we see that something might grow exponentially, right? We might see something that looks something like this. It's going to continue to grow exponentially. That is to say, it will follow an exponential curve. Well, with logistic growth, initially you start to see that exponential growth, but we start to see that over time, it starts to approach what's called a carrying capacity, if you will, right? That is to say, a somewhat of a kind of upper limit or an upper bound, if you will, as to what's happening, as to what's capping off that population, right? And this makes a lot more sense because we know that most populations can't grow without bounds, right? There's not an infinite number of resources. So if you were to look at the number of fish in a lake, for example, there's only so many resources to support a set amount of fish. Over time, there just aren't enough resources to go around, fish die out, and the growth rate is going to start to slow down. So in a logistic model, the growth rate is jointly proportional to the current population and the difference. This is one of the big, pardon the pun, but one of the big differences here. It's jointly proportional to the current population and the difference between the current population and the carrying capacity. So we have the equation, the differential equation here that models that we use to come up with the general solution for logistic growth. So this is the differential equation that models logistic growth. And this is the equation that this here is the population function where we can determine the population or the size of the population at a given time. Now, in a separate video, I will derive this equation so it doesn't seem like this is just looking like some random formula out of nowhere. There's actually a good reason for why it comes to this. But starting with our differential equation here, we see that the growth rate is directly proportional to the current population and the difference between the current population and the carrying capacity. So Kp times m minus p. And so I give you a little bit of a hint here, but again, in a separate video, I'll go ahead and derive this, okay? So let's actually just jump straight to a problem that models different logistic growth. We have a national park and it's capable of supporting no more than 60 grizzly bears. We model the equation with a logistic differential equation where k is equal to 0.001. Remember, k is a constant. So first, let's write the differential equation that is modeled by this situation. So we know that the differential equation, we would start to say dp dt is equal to, remember it's kp times m minus p. So let's plug in what we know. What is k? Well, we're given that k is equal to 0.001. So let me put that in, 0.001. And we don't know what p is, obviously. That is our population. That's what we're going to be solving for later. But we do know that the national park isn't capable of supporting anything more than 100 grizzly bears. So that here, this is our carrying capacity. This is our carrying capacity, right? Can't support more than 100 grizzly bears, right? There just isn't enough resources or whatever other threat after that. So we have 100 there. So there's our differential equation that's modeled by the situation. So we can then use that differential equation to come up with a population growth function. But what's good for us is that we already have our general form for a population growth population or function, I should say. So we can actually just plug in what we know here. So we're going to say P is equal to, again, M over 1 plus C times e to the negative k mt power. Let's plug in what we know again. So again, we know that m is equal to 100. And we know our k value is equal to negative 0.001. So let's actually plug in a couple things. Negative 0.001. We know that m is also equal to 100. And we don't know t, nor do we know what c is just yet. Okay? So here, if I just want to simplify this a little bit, I can then say 1 plus c times e to the negative 0.1 t power. Okay, so that's the function that describes the population growth, or it'll give you the population at any given size. or at any given time, I should say. All right, there are two solutions sketched on this slope field here. And if you're not familiar with slope fields, again, rewatch my video on slope fields. But we see a slope field here, which is, again, just the graph of our differential equation. And we see two different solutions sketched on here. In one case where there's 150 bears, let me actually highlight that, 150 bears. In another case where there are just, let me just go ahead and do this, just 10 bears. Okay, so we've labeled each, right? We see the 150 bear situation. So this makes sense. Now, if we see that there are 150 bears to start out, we start out with a population that's greater than the carrying capacity. And we're already told that the park can't support more than 100 bears. So what's going to happen? We see that the rate at which this population grows actually is decreasing. That is to say, the population is shrinking over time, right? Over the number of years, it's actually not growing at all. The population is shrinking, and that makes sense. Now, when our population is below the carrying capacity, right? If we start out with 10 bears, then clearly there's plenty of resources to go around. There's plenty of opportunity for growth. And so we're going to see a growth rate that's going to exponentially increase. But over time, as you get closer and closer to that carrying capacity, as you start to approach that carrying capacity here, which is 100, right? Over time, that growth rate is going to slow down, okay? And the rate at which that growth rate is changing is going to decrease. All right, now let's sketch two more populations. So let me try a different color here. Let's do one for 60 bears, and let's do one for 170 bears. If you have the notes printed out, go ahead and pause the video right now and see if you can try those on your own. Well, 60 bears should look something like this. Isn't too bad. Trying to see that it's going to approach that carrying capacity. And let's do another one here let's do orange, for 170 bears. If we're starting out way up here, then we're going to start to decrease as well until we hit that carrying capacity. Let me straighten that out a little bit there. Okay, so we can see how we can use our slope field to model the general solutions or the population functions given a certain starting population. Now, based on this and our discussion here, it makes a lot of sense that we're going to experience exponential growth when our initial population is less than our carrying capacity, right? And we're going to experience exponential decay when our initial population is greater than our carrying capacity. Again, if we start out with a population greater than our carrying capacity, then our population isn't growing, it's actually shrinking. Okay? All right. Now, if the park opened with 10 bears, when will it reach 70 bears? Now, this is our first time where we're actually going to need to solve for a certain variable. So let's start with this. We know that our initial population is 10 bears. That's given to us. So we can use our population function. So we can say P is equal to M times 1 plus C times e to the negative 0.1 t. This is our solution from part B. Okay, and let's plug in what we know. If our initial population was 10, right? So let's swap that out. If our initial population was 10 and our carrying capacity is 100, and this is our population when we first start out, that means t is equal to 0 here. So to solve this, we're solving effectively for c. We're saying 100 over 1 plus c times e to the 0 power, which is just 1. So let me just write that as 1 plus c. And then here, after just algebraically solving, 1 plus c times 10 is equal to 100. 1 plus c is equal to 10. C is equal to 9. Now, that wasn't too bad. I will say that later when you watch my proof for how we derive the general equation or general function for population growth, in that video I'll note, I'm kind of spoiling it a little bit, I'll note that C is always equal to the difference in the carrying capacity and the initial population, and it's a ratio of that difference and the initial population. So in this case, we could have said it's 100 minus 10 all over 10, and that would still give us C is equal to 9, okay? But again, we'll explore that more in the next video. Now that we know what C is, we can use that now to solve for T. So going back to our general equation, now this time we're trying to see what T is when our population is equal to 70. So we have 100 over 1 plus, now that we know what C is, 9 times e to the negative 0.1 t power. And I'm not going to show all the algebraic steps here, but needless to say, you can either use your calculator and effectively graph this function, or we can use inverse algebraic operations to isolate t, and t should come out to approximately 30.4452 years. Now, just check that with what we have on our graph or our slope field here. Let's find where 70 bears is, okay? So if we start out with 10 bears here, let me switch back to green. Oops, let me switch back to green. If we started out with 10 bears here, we're trying to find the time approximately where it's reaching 70 bears, which looks like it's right about here. Now, is our calculation that we found, does that seem to correspond? Yeah, that does look like to be about 30 and a half years. So it seems like our solution, what we found, seems to be pretty accurate. Okay, now, next question. If the park opened with 10 bears, so we're going back to this graph, when will the growth rate be the fastest? Well, we can kind of get a general sense of it just by looking at the graph here. When we're looking at when the growth rate is the fastest, we're looking for the greatest rate of change in this function here. Now remember, we're looking at the greatest slope, so something, I would guess, somewhere right around here. The slope of the tangent line seems to be steepest somewhere around there, but let's try to be a little bit more precise. So think about this. How can we use calculus to answer this question instead of just looking at the solution on our slope field? Well, it would make sense to us that if we're trying to find when the growth rate is the fastest, what we're effectively doing is we're trying to find a maximum value of our function, dp dt. We're trying to find the max value of dp dt. When have we talked about finding maximum values? Well, using the first derivative test. So what we can effectively do is we can find the extrema of our differential equation. So to do that, we're going to take our differential equation, and we'll kind of even do this in general form if we need to, but let's take our differential equation, right? And we're going to find the first derivative of this. So to help us out, let's write this. Let's plug in what we know. We can simplify to this. And I'm just going to distribute, just because it's going to make my life a little bit easier when we're finding the derivative. So if I now find the derivative of this differential equation, this would be 0.1 minus 0.002p. Now let's set that equal to 0. And I'll spare you a lot of the calculations here, but if you move 0.1 to the other side and divide by 0.002, then you would effectively get, or you would get, p is equal to 50. So now that we know that p is equal to 50, we now need to solve for the time. So we plug p for 50 in to our function, our population function. And t comes out to approximately, pause if you need to calculate, 21.97 years. And does that match up with what we have in our logistic growth? Looks pretty darn good. It does look right somewhere around there, right? That we would have the greatest rate of change. One last thing that I'll note about this is you'll notice here that our growth rate was the fastest when p is equal to 50, and that is a fact that is always going to ring true. It is always going to be half the carrying capacity. When your initial population is less than your carrying capacity here, it's always going to be half the carrying capacity. Well, what about when your initial population is greater than your carrying capacity? When is the growth rate going to be fastest then? Well, here, at this point, when your initial population is greater than your carrying capacity, it's no longer really a logistic growth curve. It's going to be more dropping exponentially. So we wouldn't be able to calculate that question that way. All right. So hopefully this helps give you a pretty good sense of the logistic growth model and how we can actually use calculus to find things like the population and when the population is growing the fastest.